The next talk is going to be presented by Ben Cartwright-Cox. He is a system engineer in the day and bad ideas blogger on the side. His talk is going long, sending weird signals over long-haul optical networks. So you can join him on his adventure of sending weird signals many kilometers and maybe set some records for the most wasteful bandwidth utilization of optical spectrum in 2024. Have fun.
Hello, everyone. Hi, I'm Ben. This is Go Long, as introduced. Hi, I'm Ben. You may remember me from what I do in the day, which is run a networking architecture site called BGP Tools. I also spoke here before at CCC with deep dive in DOS viruses. It's a little bit different, this subject. I also did other things like BGP, playing battleships using BGP. Some people didn't like that. And some other like bloggy bits around USB drivers and HDMI magic boxes. The critical bit is that I really like knowing how stuff works. So my rule of thumb in life is that, there's two things of technology. It's either really smart or incredibly stupid. I would really like to know which one it is before I use it. So modern internet backbone infrastructure these days is nearly all optical. So networking optical kit is a really weird world. There's like three separate universes for this. There's like the devices themselves, what the devices are speaking over the electrical side. There's like the actual physical optical site. So the industry a long time ago decided that you can't possibly satisfy all people's demands for different lasers, different lengths, different like amplification. And so instead, as you see in this photo here, a lot of these are pluggable modules. So the actual switch or router just has a bunch of holes which you can plug modules into. So there's loads of modules type, there's loads of different transmission or wavelengths or colors, and there's loads of different protocols that the device can transmit out of that hole. There's also different types of fiber optical cable. Most stuff these days, I would say, is single mode. For some reason, when the CCH was rewired a few years ago, they chose multi-mode. That was an interesting decision. Ask the NOC about that. So there's normally only two real types of fiber. The average boring ISP network, for context, your journey across the internet looks something like this. Your ISP has a SFP plus port, which is a 10 gigabit port, on a switch. They have probably bought that pluggable module from a vendor or a third-party supplier. A lot of these optics are basically just made in there's probably less than 10 factories that make these optics. It's probably only about 5. They're ultimately made in the same factories. The only real difference is how much markup everybody charges on each other as middlemen. Some of them provide support too, but the switch chip then spits out some kind of signal. The optic does some relatively basic stuff to turn that into laser light. The opposite exchange happens on the other end. Data bits are exchanged, hopefully, in the same order, and cat videos are exchanged. So the thing is, these optics are surprisingly stupid. That's not entirely always true. We will briefly gloss over the existence of these pluggable optics that have full CPUs in them. For example, you can get ones that do full VDSL modems in them. I blogged one in the past about an interesting Russian vendor that had a optic that just ran a full Debian Linux environment inside. Genuinely really cool optic. I would recommend. I don't have time to go into this, but it's a fascinating piece of equipment. Probably extremely good for spying. And then there's like a similar vein of this device, which you can fit modern day like home internet, fiber internet GPON inside the SFP as well, which is, I'm sure, useful for some people who want like more compact infrastructure. So we'll ignore those because those have full computers in them. But once again, this thing is not thinking. There's not much brains in there. Once again, small caveat, they do have EPROMs in them. That's going to become relevant later, but your switch can typically read this EPROM and go, well, you didn't buy it from my vendor, so you're going to have to charge you more. So I would love to know the historical arguments of why this EPROM exists, but whatever. There's also sometimes a tiny microcontroller inside that will tell you useful information, like how bright is the light coming in. This is very useful because sometimes if you send a lot of light into the other side, it will do the optical equivalent of catch on fire, or become blinded or dazzled. So you want to avoid that, or at least you want your switch to warn you when that's happening. So obviously these days things are getting faster. So Your average faster boring ISP network is actually using a much bigger port or bigger hole on the switch called a QSFP28. They are probably using a vendor QSFP28 optic, as in they bought it from the same manufacturer of their switch. Depending on the optic, I'm going to mentally gloss over the absolute specification mess that 100 gig is. There are various chips that are used to convert the signal that the switch puts out into something that's desirable. Depending on how far you need to go, it needs to do some much cooler signal processing for special use cases. Once again, assuming you've aligned the stars, the opposite happens at the other end. Data bits are exchanged, and cat videos are exchanged at 100 or 400 gigabits. These optics are a little smarter, as I might have hinted to. The fancy ones, the way this worked in the beginning is you had these they said, hey, it would be really nice if we had 40 gig Ethernet. So they just made optics that, in a simple way, they basically just made 4 10 gig optics in one package and called that quad SFP. This is the same thing happened with 100 gig. There was basically an ability to turn, we got to the point where we could do 25 gig in a single lane, and then we just multiplied that by 4. You now have a 400 gig optic, or a 100 gig optic. Same with, you can imagine what 400 gig is made out of. So this sometimes requires advanced chips. So sometimes, due to optical conditions, you need to convert these 4 lanes of signal into one really fast signal. So this requires some processing on the actual pluggable side. Actually, really quite impressive processing. Like if you have an Intel laptop, the chip in this chip in this module is probably smaller on a process node than the chip in your laptop. I mean, it is Intel, but you know. So the optics also consume considerably quite a lot of power. So it's not just running a laser, it's also running a pretty impressive piece of DSP and computer inside of it. Depending on the optic type, these things can be very cheap, the ones that don't have brains and digital signals processing in them, or they can be very expensive, but also have the DSPs to go hundreds of kilometers. Of course, other optic types are available. I won't go through all of these because it's an exhaustion task, but there's different use cases, various different industry standards. As we go above common deployments of 400 gig, we're going to 800 gig, 1.6 terabit in a single link is on the horizon. So they're used in various places in different use cases. However, there is one big one that I think people forget about optical data transmission, and that's the home theater world. So your home theater stuff also uses a kind of optical audio transmission. If you've ever looked on the back of your computer and thought, what the hell is that little red LED thing? This is a Toslink or SPDIF, depending on which bit of Wikipedia you read. So Toslink, there are 2 kinds of people that use Toslink. So there is the genuine people who have ground loop issues. That's when you can hear the mains hum, and these things are very annoying to get rid of. And there are just people who want to look cool by using optical stuff, and I entirely get that. Toslink is remarkably slow as far as optical transmissions go. It's like 10 megabits if you spec it out as 7.1 surround sound. But realistically, if you're putting a stereo signal down it, it's just 2 or 3 megabits. The wavelength isn't really even a laser. It's just a red LED in almost all cases. And the cables are like plastic or like 1 millimeter thick. And the quoted spec maximum is 10 meters, due to the fact that the core of this cable is like 1 millimeter thick. So obviously, that's a pretty big difference compared to the world of networking, of internet networking, where we have 9 micron thick cores of glass. So the reason why this is bad is because if you have a glass tube and you send a laser down it, obviously, physics, your signal is bouncing, well, hopefully not too much, but it's bouncing around in the tube until it gets to its destination. The problem is that you never actually get a perfect entry. And so the signal just comes out a little bit wonky on the other end. And so if you send a bunch of pulses down, it's like the signal, as you go into the network, is getting ripped apart. So here's a nice little simulation of what this looks like in reality. So this is, with some parameters, is like 140 kilometers. And as you see at the end, the signal on the other side may not be entirely legible. So there's 2 ways you can fix this. You can obviously not send it as far, but obviously that's not a great answer. You can also reduce the core size, which helps stop the signal from getting bouncing around too much. This is also, it makes the fiber more expensive, but these days that's not more of a problem. Anyway, I was thinking, so these things are too stupid to care what's going in them most of the time. So could we make 10-kilometer Toslink? So to do this, we have to look at like what is on the back of these optics, or on these pluggable modules. So we'll ignore the pins that need to do with talking to the brain. We're not interested in brains here. We're just interested in going 10 kilometers or more. Basically, there is the transmit side for powering the laser. There's the receive side for powering the amplifier that comes in. And there's differential signal pins. These are the only things that we'll probably need. A friend of mine made some Osmocom experimenter boards. Just a convenience thing, but they come with a 5-volt. The modules run on 3.3 volts. My world is mostly 5 volts because I play with Arduinos at most. Comes with a bunch of nice pins and exposes it, etc. Also, critically, there's a pair of line drivers to make the signal a little bit more friendly to deal with. This basically just makes things wobble right is the best way I'm going to describe it. If you ever looked at audio and balanced audio, it's kind of the same thing. It just makes the signal harder to corrupt over longer cable runs. And given that high-speed digital environments are very noisy and very difficult to get right, this is pretty load-bearing. So if you look on a scope, audio looks like this. On a very different time scale, this is what SPDIF looks like. Kind of a normal-looking digital signal. About 2 megahertz a second. It's pretty fast. This is the rough proof of concept setup I had. Basically went onto eBay and bought some analog to digital converters and digital to analog converters and tried to see if I could make a very complicated loop. And it worked. Looked a little non-airport friendly at the end of it. And I think I did fly with this once. Bit of an interesting conversation. But it does work. And if you go and look on the scope, if you look at both sides of the transmission, you see there's a 34 nanosecond gap, which is pretty good actually, because the cable patch that I used there was about 500 centimeters. So that kind of is reassuring that there is a speed, well, the speed of light works, it turns out, which is, you say that. I say that like it's surprising, but it's always good to actually verify these things. You know, otherwise you end up, if you don't validate your pure assumptions, you end up with crazy stuff. But what if we could go longer haul? Obviously, 5 meters is still within the possibility of just regular plastic core cable. So, friend of mine, there's 2 data centers around the corner. There's Telehouse, which runs a lot of the UK internet infrastructure, and there's another data center around the corner called IP House. A friend of mine is an IP House and Telehouse at the same time, has a dark fiber between them. So I borrowed a channel off one of his multiplexers. He was trusting enough to let me stick a weird signal into his thing that runs his production network, and I'm forever thankful, given he was the first sacrificial goat. This is roughly what the setup looks like. Had a bunch of the way this stuff works is basically the lasers are shooting out a slightly different color. I mean, we're way beyond the realms of what you can see with your eyes, but I view it as colors, and most of the industry sees it as colors. Shoots different colors down. There's a prism in this box, splits out the signal on one side, multiplexes the signal into one. Surprisingly simple stuff. It does just the critical bit is it lets you stick multiple circuits down one fiber. This is great because under the ground fiber is kind of expensive. And longer haul underground the fiber is even more expensive. So you want to get the biggest bang for your buck when you're going distances. Or sometimes if you're in data centers that charge you £200 a month to have a cable just sit there, you might want to do this between racks too, but that's a separate thing. So it worked, though. The portable speaker was, I don't know what the data center staff would thought of me when they saw this, but the setup works. It was fighting against the portable speaker was the biggest problem, given it's quite loud in here. And critically as well, it didn't destroy the relatively expensive optic that puts out this nice wavelength. So reassuring. On the scope, it's a little hard to see, but you can, if you look very carefully, you can sort of see match the bit stream, and the gap there is about 11 microseconds. So if we stick that into Wolfram Alpha, it says about 2 kilometers, which is reassuring, because on the other side is a loop, so about 600 meters away. Well, that's not 600 meters. You'd expect 1 kilometer, right? But the problem is buildings are 3D, and there's a lot of patching, and things you can easily hit. I have heard a off-the-hand story that in one data center, the patch cable between one part of the data center and the other ended up being over 2 kilometers, which I don't know how you do that, but 3D space is a weird thing. So, but what if we could go longer haul? So the longer haul options typically is something called DWDM, which is like the colored stuff that we spoke before, but denser. You go from 8 channels to 32 channels. The critical bit here is that the signal itself is much more precise, and the physics involved in the laser is much more interesting. It uses like temperature control to basically put can drive the exact wavelength of the light coming out by basically making the laser cooler and hotter, depending on what wavelength is needed. So there's actually some cool physics involved in here, or hot physics. So the side note also is this works really well with a certain type of amplifier. So if you want to amplify this onwards, it just hits the right kind of frequency range that's just perfect for these amplifiers. I won't go and describe how erbium-doped fiber amplifiers work. If you look into them, it kind of feels bizarre and like a bug in physics, but I don't know. I'm not an optical physics person, but I read that and was mildly scared. Anyway, so other longer hauler options are available. So most of the time, if you are providing optical solutions for network customers, you don't want your customers to use your multiplexer directly. You probably don't trust them to send in the right kind of laser. You probably don't trust them to not accidentally pick up like a $2 eBay 5-watt laser pointer and stick it in there and blow everything up. So instead, use something called a transponder. A transponder that is basically the equivalent of something that copy and pastes a signal from one hole to another hole. The idea being is that you can hand off to your customer at a normal, cheap optic that a customer will probably have on hand, and then you can install the weird optic on your side. You can also go and replace the weird optic on your side. So my signal, or my future, these weird toslink signals will work in transponders because they're basically just copy and paste devices. However, there are incompatible long-haul options. There is something called a muxponder, or like the whole wider line system series of products, which do a lot more processing with the signal that's coming in. They do this by basically speeding up, taking in, understanding what they're having, and then muxing it into a much faster signal. So someone could be sending in like a 1 gig circuit, and it will mux it into a 100 gig beam, so you can fit a lot more customers in the same place. They still have the timing constraints, and they're not overbooking the capacity, but it's just much faster. And obviously, efficiency in the game, people like these things because they're efficient. You can make more money. So because the muxponders are actively understanding Ethernet and fiber channel and InfiniBand or whatever, if you stick Toslink into these things, they're not going to understand what's going on. So the problem is, though, is that a lot of people are deploying these because they are very efficient. And so if you're asking around in circles being like, can I borrow a channel, they'll be like, that goes as far as possible. Well, they're not going to be able to help you because they have muxponders. However, so a friend of mine, so the data center that I run in my business is over in Brick Lane in London. And then, once again, Telehouse friend has this circuit and is, once again, surprisingly trusting. I guess I didn't blow up the last guy, so, so went to Telehouse, put a little loop in, went back to the interaction one in Brick Lane, put my contraption into their mux. It worked. Didn't blow it up. Round trip time was 84 microseconds, so about 16 kilometers of glass tube. There's about 10. Oh, you had to add about 10 decibels of optical attenuation. The optics that I was using here were a little sensitive. They're kind of designed to go 140 kilometers. So if you just loop their signal back out to them, it's actually just way too bright. It'll just dazzle itself and probably burn its detector out. So you basically put in the equivalent of a optical attenuator. Makes it a little less quiet or less bright. So what if we could go longer haul? Intercity. So LONAP, the Internet Exchange in London, happened to have a spare, quote-unquote, DWM channel between London 6, which is not in London, it's actually Slough, and LD8, which is in London Docklands. So this is not only, this is intercity, and it actually also has to be amplified because it's quite far away. It's about 73 kilometers. So here is that on a map. Also here is, I am quite upset that the data center industry thinks that Slough is London. Can you tell? But critically, this is not London. This is intercity. Intercity Toslink. How are we going to do this? So, same sort of deal as always. You go into a mux. This time, the mux has an amplifier on it. You might notice there's a bit of an attenuator on this one. This is because the multiplexer amplifier also amplifies on the outbound as well. So if you loop the signal back, the signal input strength coming on the other side is crazy high. This is bad because these erbium-doped fiber amplifiers have a bit of a weird quirk with them, in that if you don't match the input signal, the other signals become a lot quieter. So if someone puts in a really big signal, all of your other signals will disappear. This is bad for uptime. So basically, you have to be very careful with matching your input brightness on these things. There are some more fancy technologies to automatically attenuate for you and try and match all these things, but I wasn't going to take a chance because it's kind of embarrassing if you call someone an outage with Toslink. If you're looping back stuff, then you've got to be a little bit careful with that. The muxes on this hand are also a little bit smarter. They can actually tell you, they can make a good guess about what you're sticking in them. So here's like a screenshot from one of the muxes here. So the frequency I'm on is in bold. It's 9550 in their lingo. And they predict, or they say that the format is 1 to 32 gig. Obviously, they're probably not in the spec sheet for silly Toslink 2 megabits per second. But, it's close enough by an order of magnitude. But it's cool. Rigged it up. So I borrowed an optic from them because they have stuff that works with their equipment. Plugged it in, and it didn't work. I double checked by bringing my own optics as well, just to check that I hadn't set something up incorrectly. Just didn't work. So it's actually interesting. This DWM optic had a much higher bar for its input-output speed. So if we use the signal generator on the scope and sort of wiggle around the frequency, you can see it develops this weird lobe. So it seems to have a minimum of 3 megahertz. Now, I said earlier that the signal I'm doing is 2.5 megahertz because it's stereo. In theory, if I managed to send surround sound down it, this wouldn't be a problem. But I didn't have that on hand. So signals, anyway, it's kind of hard to have this conversation with your vendor because this signal is so far out of scope. And they get very confused. But, it's in theory stable at 6.5 megahertz, but we can't get to 6.5 megahertz. So this is a data center trip that failed. So I was really annoyed about this. I also didn't know why this is happening, because in theory, as mentioned, these things shouldn't really be doing that much thinking about the signal coming in. It's really hard to find what chips are inside these things. If you open them up, all of the chips are burned off. If the chip markings are burned off, if you do find ones that they're not burned off, the data sheets don't exist. Very secretive industry on what part numbers everyone is using. I suspect this is because there's only a very few amount of people in the game, so they don't want to really tell each other what chips they're using. Anyway, the older optics would start working at 150 kilohertz. So there's clearly something very different going on here. So I sent a bunch of emails to a bunch of different optic vendors that seemed relatively friendly, and I got this lovely response from Flex Optics. Basically, there is a retimer in there. A retimer basically just makes sure that your pulse signals look very pulsy on the other end. So as you go further and further, as we mentioned, with the signal getting ripped apart and getting a little bit vague, these things just sort of force things to be digital signals again, is a very simplistic way of describing what they're doing. Anyway, turns out those retimers don't like really low-speed stuff, which I guess sort of makes sense. The downside is that the 10 gig optics for long-haul stuff will have retimers in them because it's needed. So, fine, acquired a brand new DWM optic for 1 gig, and also at the same time got a bunch of second-hand ones from people who don't need them anymore because it's older tech. Went to the data center. Anyway, I bought a brand new one, had a very interesting conversation, email sales conversation with this fiber vendor, and said, yeah, no, definitely no retimer in it. Perfect, work with any signal. By the way, what signal are you sending in? Anyway, it arrived. And the PCB was not necessarily a strong start. XE in the networking world is generally 10 gig. It's like an acronym for 10 gig. So when the PCB literally says XE09 on it, not looking good. You go and Google it, literally the PCB number, and you know how I said before about there's only a few factories making these things. Turns out lots of people have this PCB number, and they're all 10 gig DWM optics, not 1 gig. Guess what? Literally a rebranded 10 gig optic. They just changed the little EEPROM that said, I'm a 10 gig optic to a 1 gig optic, which I guess kind of makes sense, right? If no one's really making these anymore because no one really needs them anymore, and if most switches are capable, if the retimers are capable of also doing 1 gig, who cares? The downside to this is it means you have to basically go and do retro hardware hunting for the most boring and weird components. This is roughly what the EEPROMs look like. Some vendors just let you dump it. It's just a giant hex dump and, vendor, part number, serial, date code. Funnily enough, the date code on the naughty optic that was reprogrammed was like 2018, so they're clearly not making the 10 gig ones very often either. Yeah, inside this hex mess somewhere also has what it is capable of speaking. It didn't even mention it was capable of 10 gig. They could have easily just flipped that bit and been more honest, but oh well, whatever. Anyway, so armed with a old 1 gig DWDM optic on a different channel, which meant that I had to go to Slough and mess some cables around, it did actually work. It's really hard when the round-trip latency is 720 microseconds to find that on the scope. So the solution I came to was just tapping the inputs and seeing at what point did the waveform look like it's changing. Anyway, assuming this is a normal way of testing latency, it's about 750 microseconds, which speed of light roughly in glass is 143 kilometers. This is a very relatively long-haul link. This is what the testing setup looked like. You're never really sure on these long-haul links, like if these are being, I don't know, conspiracy theory mode, but like these could be tapped by someone. So I gave them a nice little gift. I like to think that like someone. In the back of my head, I like to think that somebody saw this signal and was like, I don't know what it is, decode it. It seems to be a Toslink signal. Play it on the speakers. And then someone orders the bombing of Slough or something, I don't know. Anyway, this is such a long-running project. I'm so glad that it finally got done. There is, of course, always future innovation you can do. So in theory, if the actual module if the optic didn't have logic to make the square wave even more square, we're ignoring the retimers. You could actually just send raw audio straight down. There's nothing stopping you. It would probably make the laser unhappy, but short-term gains. This is kind of how RF over fiber works. Some networks are sort of stuck between running cable TV over optical stuff because that suits their migration agendas. So you could sort of reuse these optics. They're very different. They put different components inside. You could also, apparently, YOLO an FM signal straight down this. It's not going to sound very good, but it probably would resemble music. The other thing you could do is attach a dial-up modem to both sides. This would probably create the biggest waste of bandwidth of optical space. Something that could probably run 25 gigabits would link up at probably 40 kilobits. Also, I assume this would completely blow the minds of somebody who's tapping the signal. So what have we learned? You can send low-speed signals over these optics. Sometimes, of course, some optics have standards, but most of them don't. You sometimes, with the right equipment, can send them really far. There's not a good reason to do this. There are IP solutions for almost everything that you could possibly want to do with this now. If you're sending audio specifically, there's modern-day things like Dante or AES, I can't remember the last two numbers. But knowing how things work is really important. Knowing stuff around how the core of the world is built lets you build much more exciting, much more horrifying problems at the times of great distress. It's not necessarily honorable, but it could work. I know way more about optical transmission than I did when I started, and the general workings of how my industry sends bits around, a layer that I don't really operate on very much, and maybe you do too. And with that, I would like to thank you, and are there any questions?
Thank you very much. So if you have any questions, please line up at the microphones. They are around the room. You will find them, I guess. And we already have a question from the internet. The internet, please.
Yeah, there is a question. Is there an easy way of determining whether an SFP optic has a microcontroller in it?
I wouldn't say they all have microcontrollers in them. Probably based on date, I would say that sometime around 2010, they all started having microcontrollers for the laser light reading stuff. Fun fact: the way this is actually implemented is it just extends the EEPROM. So your EEPROM gains another page with data that is not actually writable. Yeah, it's a weird implementation, but I guess everything is hacks. So, yeah.
Thank you. And we do have a question at microphone 1, please.
Yes, have you tried actually improving your toslink signal by making the rise time shorter by a small differentiator circuit before it? Or
yeah, I feel like that's so there's many ways you could, for example, you know how I said it didn't work in mux sponders? In theory, you could stick an Ethernet preamble in the front, and it might work on the other side. I feel at that point you're kind of corrupting the spirit of the scheme, because you've kind of made Ethernet-y toslink. Yeah, some switches, for example, will let you do 100 megabits, even though they're like 1 gig fiber switches. And the way they actually do this behind the scenes, is they just repeat the frame 10 times. And the other side is running too slow to not notice that this is happening. So I feel like at that point you're sort of corrupting the scheme. But you could definitely do a lot more tricks to improve the signal quality. Thankfully, Toslink is very forgiving, so that wasn't necessary in this case.
And is there another question from the internet? No question from the internet. Then please, microphone 1, go on.
Did I understand correctly that optical cables have electrical couplers, like sometimes we in electrical cables put in optical couplers?
I don't necessarily understand your question.
Like, if you connect the device, we sometimes put an optical coupler in the way that we don't burn out the device if something's corrected stupidly.
Yep.
So we put electrical couplers in optical cables now?
Well, yeah, sort of. One is fixing like an EMI, problem, and the other is fixing a customer problem. The customers, I think, are much more dangerous.
Thank you. The next question from microphone number 4, please.
Hi, thank you for the presentation. SFP is also used for copper pairs. So I was wondering if you think your experiment would work also on copper pairs, or is there any difference?
Yeah, so I'm not going to try and do that. Basically, the way those base T optics work is kind of horrifying. So it's there's basically if you look at the power consumption of those things, they're like very high. If you ever touch one of those base T things, they're like super hot. That's because there's a fast DSP running there. The copper pair standard is pretty different to the optical standard. So there's basically just a DSP chip desperately trying to convert between the two. And it does a very good job, but it's a very different set of technology. If you send Toslink down this, it has no idea what's going on.
Okay, thank you.
And microphone number 3, please.
Hi, thanks for the talk. We happen to have some equipment in New York. Would you... Would you like to recall some underwater submarine device?
So submarine cables are kind of interesting because I don't know what submarine cable you're on, but most submarine cables these days have basically a forced mux sponder on them. So maybe this can work. I wouldn't mind potentially, causing the funniest error on their side. But the sad thing about I was hoping that someone would ask about what about under the Atlantic. So the sad part about this is that had I done this maybe 10 years ago, there were still a couple of cables left that weren't just entirely mux sponders on both sides of the cable. These days, as far as I understand, when you buy raw submarine capacity, you're basically playing a game with the mux sponder on the other side. So you have no choice. You have to set very specific framing timings. These things run extremely fast. And if you send 2.5 megabits down, I'm not even sure if the laser can stay on for that long. So I think it would get very unhappy. I'm willing to try. I was speaking to
So maybe a talk for next year or the year after next year?
Anything is possible.
There is another question on microphone number 1. Please go ahead.
You talked about the possibility of connecting a DSL modem to it. Do you plan on doing that anytime? or?
Yeah, I mean, I have a couple of the boards ready to go. I just need to find weirdly, I don't have a dial-up modem handy, and I think you'd have to probably modify it quite a lot. I think the telephone system runs at quite a higher voltage than what this thing would want to do. But yeah, I mean, there's no reason you couldn't do this. I just haven't gotten around to it. The problem with most of this presentation is that what you don't see is every time I went longer, that was probably like a 3-month sort of finding people in pubs in my industry and saying, hey. So at the end of this, it's you're pretty happy to just finally have done 140 kilometers. And of course, between that and many people going false starts, right, where people are like, oh, actually, sorry, I have a Mux sponder on the end. So you could do it, and it's tempting. Who knows? Maybe follow me on Fediverse, and maybe you'll see one day me creating the biggest waste of optical bandwidth possible. Well, not possible. You could go worse.
Thank you. Is there another question from the internet? Any more questions in the room? I don't see anyone heading towards the microphones. So let me say thank you very much for this nice talk.